We want to now consider the case where we have a non-constant amount of force applied to an object. In this case, we want to consider a block on some, in this case, frictionless surface to simplify the case, and attached to a spring. We know that the force of a spring, an ideal spring, follows this formula known as Hooke's law, and the main properties are this letter K, the spring constant, describes basically how much force you're going to get depending on how much you stretched it. X here, which is the displacement from the equilibrium position, equilibrium point where then there'd be no force from the spring acting on the block. And this minus sign, which is telling you that this is a restoring force that's trying to return it back to its original position. So if we want to do a proper free body diagram, we would have the weight of the block, the normal force, and then the spring force, which could be in the x direction, either positive or negative. If we'd assume that the displacement, delta x, was in the positive direction, then we would expect the spring force to be in the opposite or negative direction. So we would expect in the y direction that the net force to be 0 and the normal force, the gravitational force, to be the same. And again, we're going to ignore the effects of friction to simplify things. So in that case, the net force in the x direction would just be the spring force. And we also know from Newton's second law that the sum of the forces is supposed to be the mass times the acceleration, again in the x direction. So to simplify things as well, from now on when I write acceleration, it'll just be in the x direction, so I'm going to just drop the subscripts of x. So if we go ahead and plug in our force of spring, then we know that we have minus kx is equal to mass times acceleration. In this case, clearly the acceleration is not constant. It's going to change with the position of the mass. And in fact, this is actually a differential equation, because we know that the acceleration is equal to the derivative of velocity with time, which itself is a derivative of position, so this is actually twice derivative of the x position as a function of time. And also I'm going to introduce a little bit of a scripting that you may have seen in some other cases where I have these little dots above x. Each of those dots means a derivative with respect to time. So acceleration is equal to 2 time derivatives. So another way of writing this is then minus kx is equal to mass times x double dot. So that's a differential equation. We're going to need to find a way to solve it. One thing I'm going to do is just one little bit of algebra and have the second derivative on one side and all the other stuff on the other. So x double dot is going to be minus k over m x. And I'm going to make this a little bit nicer that k over m, I'm going to give a particular label so I don't write it over and over again. And I'm going to give it the label of omega squared. Now, seems a little bit odd that I would actually make it equal to some variable squared, but I'm making this whatever I want to be, so you can't stop me. More importantly, though, you'll see that it'll become a little bit more useful later on. If I plug that in, though, I'll get x double dot is equal to minus omega squared x, and omega squared, remember, is going to just be some constant. So now think to yourself, what function has time as its variable, and if you took the derivative twice, you would get the same function to pop out, along with some constant and a minus sign. So, more broadly, first think, what sort of functions do you have that you could take a derivative and the same function pops out along with some sort of constant? And then if you did it again, what would pop out? So you might think, for example, well, if I had e to the alpha t, and if I take a time derivative of that, popping out I would get alpha E alpha t. So again, the function was E alpha t. It pops out again here after a derivative, and then there's a constant. Do that again, and you would get that constant squared, but it wouldn't bring out the minus sign. On the other hand, if I had the function, say, cosine alpha t, and then I took a derivative, I would get minus sine alpha t, also multiplied by alpha. So it's not the same function since cosine and sine aren't the same function, but if I take the derivative again, I will actually get minus alpha squared cosine alpha t. So look at that. With the cosine function, take two derivatives of that, I get the same function to pop out, a constant, and then this minus sign. So I can actually say that this broad sort of function will work, and without any real hard proving, actually, I can say that the function of x as a function of time should have the form of cosine omega t. And to make it more general, I should also include this thing I will call the phase constant. It has no dependent on the t function, but if I take the derivative, it doesn't come out of the equation, so this makes it more broadly true. And also this equation will be true if I also have any other constant multiplying by it. So this form of the equation is the most general form that would fit this differential equation. And you can see if I take the derivative of this function twice, I will get acceleration. It'll be in the same form here with this omega squared there and a minus sign. What this means now is that I have a function that describes the position of the object at any given time, and all it's going to depend on is the omega value here, which we see is related to the spring constant and the size of our mass. We see that there's this thing here called we could call the amplitude. It will say how big this is, and you can see why it would describe amplitude well. Since cosine, this function, can only go between plus and minus 1, a will then tell us basically how much it's going to oscillate up and down. It will go anywhere from negative a to positive a. So amplitude then of a wave. Cosine function, we know what that looks like. It's going to basically have this sort of form on the xy plane, or the xt plane. Now also then, this phase constant is in a sense going to tell us about the starting position. I plug in a certain value of phi here, and that will actually shift the function left and right, and you would see then that would affect where the function is at time 0 if this thing were shifted left. So in a sense, this is going to act almost as if it were the x naught position in the kinematic equations you've used before. But let's ask ourselves a little bit more about this omega value. What is it really supposed to be then? So we said omega squared we set as to the spring constant divided by the mass. Or we could put this another way, that omega is equal to the square root of spring constant over mass. If you look at the units of this thing, you are going to see that it has units of inverse seconds, or another way we tend to call that hertz. So what this thing represents is a sort of frequency. It's not the same sort of frequency that you might know from sound and the like, but it's definitely related. In this case, we will call this the angular frequency. And the reason it's called this angular frequency is because since it's found in the cosine function, it's telling you how much time is going to take, or what sort of frequency it has for the oscillation to complete through the cosine function. How quickly you can go through the unit circle. And this would then means we need to affect its relationship to the frequency you might know a little bit better. So to get that relation down, the way we define things is we first talk about something called the period. And we tend to use the capital T for period because obviously the word period begins with T. Now, and more because of its relationship with time, and I guess P has already been used up. We've run out of letters is the real excuse that we're going to have to use here. But T is going to be period, and its relationship with the angular frequency is going to be 2 pi divided by omega. What this basically means is that 2 pi is representing the 2 pi radians of the unit circle, and then omega is basically how fast it's going to get through that circle. So the larger omega is, the smaller the period is going to be. Now, period also has a relationship to the frequency that you would know. So frequency in hertz that you know is just the inverse of the period. Now, frequency is defined as basically how many times you do something in 1 second. And that's exactly then what's going to be happening here. So we have, right now, unit time, or the period has units of seconds. Now it has units of inverse seconds. So how many times something happens per second. The period tells you how long something takes. Putting this way, it says how long it takes per second. And then from our definition here, the relationship between frequency and angular frequency is just omega divided by 2 pi. From the physics that we want to consider, if we went back to our period function here, and period is usually the more easy thing to measure, if we looked at that, we plug in omega, we're going to see that the period is going to be 2 pi multiplied by the square root of m divided by k. Now, again, m is supposed to be the mass of this block on that spring. K is the spring constant. And this might fit your physical intuitions. If you have a really large mass, it's going to take longer to do this sort of oscillation. Well, if you have a spring constant that's very large, a really tough spring, it's going to have a lot of force and it's going to really accelerate this thing back and forth. So we see that there's now this nice direct relationship between two relatively easy measurements that we can make in the lab and the period that oscillation is going to take. So already now from our differential equation we can now describe where a block is going to be, how fast it's going to go back and forth and do any sort of complete oscillation, and we also then can relate it all nicely to physical quantities that we can measure in the real world. In this simple example that we have, what we have described is what we would call a simple harmonic oscillator, and often we'll talk of simple harmonic motion, or SHM. And the simple harmonic oscillator, while of course describing a spring system, is something we use in physics in many different circumstances. And sometimes we try to cheat and say something is a simple harmonic oscillator just because we can do the physics for that really easily. One of the things that will be a bit useful as well is that with simple harmonic oscillators there's a nice way of dealing with energy and such oscillators. We know that springs can do mechanical work, we know the forces involved, and it has been shown to you before the energy in a spring, how it relates to how much it's been stretched. That the potential energy in a spring is related to 1/2 k x squared, where x again is the displacement from the equilibrium position. And since the energy in some sort of harmonic oscillator should be conserved, if we were again in this frictionless case of a block sliding back and forth across a table, then the potential energy will go back and forth between that and kinetic energy, and the maximum amount of energy in that system will depend on basically what's the maximum amount that spring can be stretched, because when it's at its maximum point, it will have stopped momentarily and then come back. So at one instant, it'll have all potential, no kinetic energy, and at that instant, it's also at its amplitude point. So we know the energy in an oscillator is equal to 1/2 k, the spring constant, times the amplitude squared. So we now have this great way of dealing with harmonic oscillators and knowing exactly how much energy is in them, and from the way the motions are, we can describe how the energy evolves back and forth between kinetic and potential energy.